Hi everyone. I hope everyone's healthy and well. Thank you for joining us for the next talk in our Golden Webinars in Astrophysics series. My name is Evelyn Johnston. I'm a postdoc at the Institute of Astrophysics at PUC, and together with Thomas Putzia, a member of our faculty and head of outreach, we will be organising this series of talks for as long as we can. First of all, we'd like to thank you all for your overwhelming response and encouragement. We really appreciate your comments and suggestions, so please keep them coming. We will continue to bring you these talks in the original English and simultaneous Spanish translation without any registration fees. This has been made possible by the generous support of the Center for Astrophysics and Related Technologies, also known as CATA for the Spanish acronym. Our talk this evening will be given by Jill Tarter, who is the Director Emerita for the Search for Extraterrestrial Intelligence at the SETI Institute. But first, though, we'd like to give you a brief introduction as to how the seminar will be run.
We have arranged for simultaneous language interpretation provided by Mr. Patricio Gonzalez, Director of Serendipia Soluciones, who will be simultaneously translating for us in both English to Spanish and Spanish to English directions. On your devices, you can switch between the English and Spanish channels using the interpretation button at the bottom of your Zoom window. Unfortunately, the live interpretation option is not offered for people using Zoom in the browser or on Linux machines. We're really sorry for this, and we will post both English and Spanish versions of the talk on our Astrofísica YouTube channel very soon after this webinar is over. We've also heard from a few participants that they could not mute the original soundtrack when listening to the Spanish translation. So if this is too confusing, please just simply leave and rejoin the webinar. So this should simply fix the issue. If you have any questions during the talk, please type them in the Q&A window. All viewers will be able to upvote questions and comment on them. We have a team of astronomers and journalists behind the scenes who will be monitoring your questions and select the best questions for the discussion after the talk. talk is expected to last at least 45 minutes, and we will have time for questions and discussions at the end of the talk. The questions from the audience will be selected only from the Q&A window, not from the live stream on YouTube. So please type them in the Q&A window if you have them.
Before we begin, I'd like to briefly introduce our other panel members who are with us today. So we have myself and Thomas, we have Patricio Gonzalez, who is our interpreter. From the faculty at the Institute of Astronomia at PUC, we have Nelson Padilla, and also from our students and postdocs, we have Giuseppe Dago, Paul Eigenthaler, Jennifer Fienco, Alvaro Valenzuela, and Sergio Best. We also have the great pleasure to welcome our guest panelists this evening. We have Katerina Kravchenko, who is an ESO postdoc or an ESO fellow here in Santiago. We have Tim Abbott, who's the telescope scientist at Blanco at CTIO. We have Hans Zinnecker, the astronomer emeritus and ex-deputy director of the Sophia Science Center at NASA Ames, and Leopoldo Infante, who is the director of Las Campanas Observatory. And finally, we have our excellent team of Q&A managers, Ricardo Acevedo, Daniela Fernandez, and Carol Rojas. It is our pleasure today to introduce Jill Tarter as our speaker this evening. Jill's career started with a degree in engineering physics at Cornell University, followed by a master's and PhD in astronomy at the University of California at Berkeley. She completed her PhD in 1975, and in her thesis, she used the term brown dwarf to describe small mass objects that fail to stably fuse hydrogen. I believe this was the first time the term brown dwarf was used in the literature, though I could be wrong. After her PhD, Jill carried out a postdoc at the NASA Ames Research Center before moving back to the University of California in Berkeley as a research astronomer. In 1989, she became a project scientist. Pardon? In 1989, she became project scientist for the NASA SETI Microwave Observing Project and High Resolution Microwave Survey. And in 1993, she was appointed the director of Project Phoenix. Since 1999, she has been the director of the Center for SETI Research. And between 2011 2014, she was the adjunct professor at the Department of Physics and Astronomy at USC.
Many people are probably familiar with her work as the character portrayed by Jodie Foster in the movie Contact, which was based on Jill's career and work, though I believe Jill never spent the time sitting on her car bonnet listening to the signals from SETI through a pair of headphones. Okay, so please eradicate this vision from your mind. Funding for NASA's SETI program was unfortunately terminated in 1993. And since then, Jill has served very successfully in a leadership role to secure private funding to continue this wonderful exploratory science. Throughout her career, she has received many awards, including 2 NASA Public Service Medals. In 2012, she was named in the Time 25 Most Influential People in Space list. So now we would like to hand over to Jill to tell us all about her work on searching for aliens and finding ourselves. Jill, please go ahead.
Okay, thank you, Thomas. Let's see if we can get this share screen to work. Did we get it?
Yes, we did.
Good. All right. So it's really a pleasure to be part of your series. It's so well produced. And I'm going to try by the end of our time together to change your point of view, perhaps, to try and let you see yourself and understand yourself in a larger context, because I think that that's going to be incredibly important in the years to come as we try and solve some of these global challenges that we're facing. So let me start with now I think I have to click on that and get it woken up. All right, I usually don't give such an elaborate introduction for myself. I just note that I work with a team that uses radio telescopes that are trying to find extraterrestrial technology. And I'm the one that doesn't wear the headphones, right? So as you've heard, I have degrees in engineering physics and astrophysics. I've only really had one job my whole career. So I started as the NASA SETI project scientist and then became employee number one at the SETI Institute, and then director of various research projects that we held. And I've been the past president of the Cal Academy of Sciences. I got my first honorary degree from the University of Pennsylvania last year. And although I'm retired, I'm still cheerleading for this exploration, which I think is incredibly important. So before we start talking about finding them, I think it's necessary to put us in a proper context. So where are we and when are we? Well, where are we? Sure, it's easy, we're here. So like most of you, I'm working from home, which happens to be on Shasta Road in that house in the Berkeley Hills in the San Francisco Bay Area. And from the altitude of low Earth orbiting satellites, we'd see ourselves here on the west coast of the United States. And of course, since 1968, when Bill Anders, the astronaut, took this beautiful Earthrise image, we've been for the first time able to see ourselves in a larger context of our planet hanging there in the darkness of space. And in the summer of 2013, I hope you got the memo and went outside in your best clothes and waved at the Cassini spacecraft, who managed to take this selfie of all of us here on Earth on that little white dot at the end of the arrow. Yes, there is a dot, and that's all of us right there. And earlier, Carl Sagan got the Voyager 1 spacecraft as it was passing by Neptune to turn around and take a look and make a picture of us, this pale blue dot that's been made so famous. So we're here too. We are one of several 100 billion stars in a grand spiral galaxy like the Milky Way. Now, I don't have any spectacular technology that allows me to pop up out of the galaxy and take an image, but this is what we have thought the Milky Way would look like if we could do that job. This is M101. But indeed, although we can't take an image like this of the Milky Way in the optical, we can, in fact, measure the galaxy from the inside out using radio telescopes and something like 5,000 hours of time to map out water masers and methanol and CO2 gas. So this was completed this past spring, and indeed, our galaxy does look quite like M101. So we're here, one of hundreds of billions of stars in the Milky Way galaxy. And our galaxy is here in the Hubble Deep Field. And there are hundreds of billions of such galaxies across the sky. And you can notice that some of these points of light, which are galaxies and not stars, some of them are dimmer and smaller because they are farther away. So this reminds us that as we look deeper out in space, because of the tyranny of light speed, we're also looking back in time, which means that we're now, right, at the end of something like 13.8 billion years of cosmic evolution. And what I'm going to try and convince you of is that we are intimately connected with long ago and far away events in this expanding cosmos. So we humans trace our lineage not just back through the hundreds of years of our families, and not just back through the millennia of human civilization and its arts and its many experiments with governance. We trace our heritage not just back over the millions of years since we branched off from the great apes, not just back the 2.4 billion years during which the Earth's atmosphere has been perfused with oxygen thanks to the photosynthetic labors of these blue-green cyanobacteria. And not just back to the 4.6 billion years ago to the formation of our planet and the solar system, we need to go back millions of years before that, back to a large giant molecular cloud that was contaminated by the winds of Wolf-Rayet stars and the debris from supernova explosions, such as this beautiful example, modern example. And the reason is that the iron in the hemoglobin molecules in your blood, the calcium in your bones, they were literally cooked up deep within old massive stars that ended their lives in these catastrophic explosions that we call supernovae, and leaving behind remnants like this modern example that become incorporated into the next generation and in our case, into our solar system. And hopefully that kind of recycling will continue for a long time to come. So this debris turned into stars and planets, and in our case, life, and perhaps somewhere else, that same cycle will be replicated. So the long story is summarized with this very short quote, which is that it really does take a cosmos to make a human. And we are, as Carl Sagan told us, literally made out of stardust. And we have taken about a millennia for our scientists to piece together this story. And we're not finished yet. We're continuing today on this journey to understand more. We're driven by curiosity about who we are, why we are, what else there might be, and of course, who else there might be out there. So when you're talking about trying to find life beyond Earth, there are a number of ways I think we might be successful in this century at that task. You can discover it. Within our solar system, you can explore for in situ biomarkers. We, with big enough telescopes, can in fact do chemical assays of the atmospheres of planets orbiting other stars and look for biosignatures, kinds of disequilibrium chemistry that we don't think could be there unless there were biology of some kind on the surface of the planet. You can try and communicate with it. That's what SETI is all about. We're looking for technosignatures. So it's called the search for extraterrestrial intelligence, but we can't define intelligence. We certainly don't know how to detect it at a distance. What we do is we use technology as our proxy for intelligence. And then we go looking for some technology that's modified its environments in ways that we can sense over the distances between the stars. And these could be deliberate observations, or in fact, they might be some serendipitous discovery on the basis of looking at the universe in a new way with new eyes, new tools. And finally, we can export it. We're beginning to talk about back to the moon, onto Mars, perhaps the asteroid belt. And Breakthrough Starshot is trying to figure out how to accelerate little 1 gram sensors, enormously capable sensors, to 20% the speed of light and send them to the Proxima Centauri system in order to explore, looking for technologies and looking for biology. All right. And then there's Mae Jemison runs something called the 100-Year Starship Study, and Project Icarus, again, trying to figure out how you could boldly go. So that's the story about life. I think one of those bets is going to pay off in the not too distant future. And so over my career, there have been 2 game changers, really important game changers. One is extremophiles. The other is exoplanets, and now perhaps exomoons. So extremophiles are forms of life that live in environments that we couldn't possibly tolerate, we humans. But there are all kinds of organisms, and not just microscopic. The picture with the red there, those are the giant tube worms that are growing at the bottom of the ocean around black smokers. But we have organisms that live deep underground with no sunlight. We have organisms that, such as the tardigrade, that can withstand total desiccation and vacuum conditions. And we have organisms such as the radiodurans on the right there that can withstand radiation environments such as this cooling water in a nuclear reactor. So these organisms are beautifully adapted to conditions that we couldn't survive, but that they find perfectly wonderful. And that is driving us to explore other places. So this is not the Mojave Desert, this is the desert on Mars, right? And we know that Mars was once wetter and warmer, and we are beginning to explore, and the SAM instrument on the Mars rover actually has found compelling evidence for organic compounds by drilling into rock formations such as the sedimentary rocks here. And so we know that there once was a lot of water on Mars. It was wetter and warmer. And now we know that there currently is water on Mars seasonally with these recurring slope linii. And this actually complicates our exploration of the planet, because we're pretty sure that on the desert, on the surface, any biology that we bring along on our spacecraft will not be able to reproduce and grow. So we can't contaminate Mars there. But where there is the opportunity to have liquid water, then microbial life that we might bring with us could, in fact, potentially reproduce. And we want to make sure that any microbes that we discover on Mars are Martians and not what we brought with us from Earth. So there is this big problem about forward contamination, and if we bring samples back from Mars to study in our laboratories, we don't want to have back contamination as well. So the most interesting thing that we might find with our exploration for life on Mars is evidence of a second genesis, a second start of life that's independent and unrelated to life on Earth. We know that planets swapped rocks early in the formation of the solar system. So it's possible that a microbe cocooned safely inside a piece of rock that was chipped off Mars and landed on the Earth could have possibly brought life to Earth, or vice versa, from Earth to Mars. And so anything that we find, we are going to be examining closely to make sure that it is indeed a second genesis and not just evidence of panspermia. So Mars is the most obvious place to start looking for life, but it's not the only place. Jupiter and Saturn have these large icy moons. And because of the gravitational tidal interaction of these moons, they are icy on the outside, but there are salty liquid oceans underneath the ice. And we were startled not too many years ago with this little pipsqueak moon at Enceladus. And when we imaged it with the Cassini spacecraft, we found that at the south pole of Enceladus, there are these cryovolcanoes. There are these plumes, which is spraying out from the planet samples of the liquid ocean beneath coming out through the crusts. There are apparently also such plumes on Europa, but these seem to be less reliable. And so if we're going to do a plume mission, if we're going to try and fly through these plumes and scoop up and concentrate the material that we collect, looking for evidence of some kind of biology, Enceladus is my favorite target. So we may, in fact, in looking for life, have to go beyond the solar system. And when we started SETI observations, we had no idea whether there were any planets around any other stars. We knew of the planets in our own solar system, and that was it. But thanks to ground-based telescopes and particularly this Kepler spacecraft, we now know that planets are plentiful. In fact, we know statistically that there are more planets than stars in the Milky Way galaxy. And this is such an incredibly huge change of perspective from the beginning until our current viewpoint. And we're finding that there are planets orbiting other stars that are unlike any that we have in our own solar system. Super Earths or mini Neptunes. We don't have any of those. Maybe we did at one time and they were ejected from our solar system, but they are plentiful elsewhere. And indeed, the closest planet that we could possibly find is around the closest star to the sun, and it's Earth size, and it's in the habitable zone, which is why Proxima b is such a compelling target for early explorations. And of course, not too long ago, a couple of years ago, we woke up to the New York Times with a system with 7 Earth-sized planets orbiting a small red dwarf star. And this system is extraordinarily compact. The star is much less massive than our sun. And if you put this system, the TRAPPIST-1 system, into our solar system, all of those 7 planets would fit inside the orbit of Mercury. So this is a very intriguing system, and it was found by transit observations, the kind of thing that Kepler was doing as a spacecraft. This was done from the ground. So when these planets pass in front of the star, they block a little bit of the star's light. And we can look at these transit events and with enough data deduce that those planets are in fact there, although we have never seen them, right? So nevertheless, we take advantage in SETI of this system, and we look for conjunctions of 2 of the planets and our telescope. And so we just sort of make an assumption that if multiple planets in this system were occupied, there might be some interplanetary communication going on. And so we wait until they line up in a direction that we would be looking right down the communication path and observe with our SETI instruments, looking for technological signals rather than astrophysical ones. So we not only want to know whether any of the real estate is actually habitable, we're interested in knowing whether it is inhabited. But at the moment, we don't know very much about any of these exoplanets. We know a few things. We know their periods, their semi-major axis, their radius, and sometimes we know the mass from radio velocity studies combined with the transit detections, which will give us the density of those planets. But it doesn't tell us what they're like, whether they have a climate, whether they have oceans, etc. I think the best that we're going to be able to do is figure out what the upper limit in mass is for a rocky planet in these systems. And we want, of course, to know more. And we will. In the future, both ESA and NASA have this incredible suite of instruments that they will be orbiting to study exoplanets. And we are building these large ground-based telescopes, some of whose time will be spent examining exoplanets. So this is a fantastically exciting field that is just exploding. And for me, I love it because this was not a science that existed for centuries. So it was not a science that was in a silo and completely occupied by, old white men, right? So the exoplanet science is being populated by fantastic young people with lots of great ideas. And for me, the thing that I like to see is that a number of those, and some of the best, the very, very best, are young women. So I'm all for that. So when we begin to talk about looking for signs of someone else's technology, we need to be careful about our language. So I've already admitted that we don't know how to define intelligence. So that I is there in the acronym, but indeed what we're looking for is technology, and that's our proxy for intelligence. So if we find something that has been astro-engineered in some way, we will assume that at least at some time there was some technologists with intelligence who created the technology. So, and on the other hand, what's technology? How broad can we get with that sort of definition? And we've taken it to mean the ability to deliberately modify an environment in ways that can be sensed over interstellar or interplanetary distances, including unintended consequences. And also, SETI is not SETI. SETI, C-E-T-I, is what the Russians initially called this exploration. And they meant communication with extraterrestrial intelligence. But before we can communicate, we have to find it. And so SETI is actually the exploratory part of trying to find evidence that someone else has a technological civilization. So we're looking for technosignatures. Right? And historically, starting back in 1960, we've been guided by these 3 laws of Arthur C. Clarke, science fiction writer and a good engineer. So Clarke told us that when a distinguished but elderly scientist states that something is possible, he's almost certainly right. When he states that something is impossible, he is very probably wrong. And I have to say, Arthur Clarke was using that he deliberately and not generally. So since I'm a she and not a he, I expect you to believe everything that I tell you, right? The only way of discovering the limits of the possible is to venture a little way past them into the impossible. And that's what we do incrementally all the time as we build these bigger and better tools, computers and telescopes. And then the 3rd law, any sufficiently advanced technology is indistinguishable from magic. And that's what has been driving our SETI searching since 1960. We're basically looking for the technologies that we understand, but on steroids. We're projecting how they might get stronger and more powerful and more detectable in different ways. But it's actually been recently pointed out to us by Carl Schroeder, who's an environmentalist and a philosopher, that really, if you're going to be a sufficiently advanced old technology, you need to be indistinguishable from nature. You really can't be so out of equilibrium and so dismissive of resources. You need to be sustainable for a long future. And so an advanced technology will find ways to conserve resources and husband its planet well with great efficiency and no waste. So what might we find? What might natural versus engineered to be natural look like as we get the ability to actually begin to image some of these exoplanets? What kind of technosignatures might we find? All right, we might find unexpected albedos and glints in these coming from these planets. For example, if they are, if they have a large, if the planet is tidally locked to its star, and they might have decided to orbit large mirrors to illuminate the dark side, the far side of the planet. The surface temperature might just be wrong for what we think we understand about their distance from the star, the host star's spectral type, and our best guess at what an ocean or a reflective rocky crust albedo might be. A long-term technological civilization would probably try to engineer out any extreme weather, although I'm not quite sure what the observational consequences of that would be. You might find that they are willing to invest a great deal of energy in keeping latitudinal homogeneity, because they don't want to be living in icy poles or really hot equator regions. They might, in fact, want to equalize their climate. It takes a huge amount of energy, that would be for sure. And whether that's possible to do, I don't know. And could we ever detect that homogeneity from a distance? That's a question. And you might find that in a system such as TRAPPIST-1, where there are many planets in short period orbits, we might, when we finally get the ability to image TRAPPIST-1, we might find not the artist concept of what the planets would look like, but we might find this, that they had all been geoengineered, bioengineered, to give more habitable real estate of a particular type that is enjoyed by the technological civilization. Arthur Clarke was the one who first brought the concept of geosynchronous satellites to our world. And so what if this technology on a distant exoplanet has just built up this incredible exobelt? So not just a geosynchronous ring, but giving some vertical scale to their orbital geosynchronous or planetary synchronous technologies. If this were dense enough and big enough, high enough, thick enough, we actually might be able to see that in the light curve of the planet. And another idea is that if you start to do this astroengineering, megastructure construction around the star in order to capture more energy for whatever you want to do, you will actually begin to modify the spectrum of the star. And so we might be able to detect at a distance this kind of technosignature. So, no, we're not going to take a break because I'm going slower than I had wanted to. So, what can we do? We've been looking for electromagnetic signals now for decades. We can also start looking for artifacts. And that's really going to be feasible only within the solar system. On Earth, artifacts would persist. You can make a historical search through literature and documents back for a few thousand years. Archaeology takes us back a few 10,000s of years. And geology will allow artifacts to persevere for 100 million years or so. And then recently, it has been suggested that you can look for, in our solar system, you can look for neutrinos as energy, as information carriers. And you don't find the neutrinos themselves, but you can find that in your lab, the decay rate of manganese 54 can be modified by the presence of a neutrino stream. All right, so the moon, well, we would have missed anything that was subsurface or less than 10 meters in scale so far with our observations. How about the asteroid belt could contain artifacts and that might have transmitters on asteroids that are in the radio or the optical or the infrared. The Lagrange points of the Earth-Sun system have been postulated as likely parking places for someone who has a probe that is going to patiently await the awakening of our own technology. And near the L4 and the L5 points, something called Kartolewski clouds appear to have been observed. And I say that because some people can see them and others can't. But it's been suggested that perhaps those clouds are probes that are made by molecular manufacturing, and they're little diamondoid robots. And so we should try and investigate those special points in our own solar system. And of course, it's been suggested that comets could have technologically created ice flowers in order to present manufactured technology. So I said that this is only feasible in the solar system, but when Oumuamua came by a while ago, we all thought back to Arthur Clarke's Rendezvous with Rama and wondered if that could be an interstellar spacecraft. And so we all observed it. And because these visitors from outside the solar system will be detected with increasing frequency in the future, perhaps I can actually remove that caveat, and this kind of interstellar visitor might allow us to look for artifacts from someone else's solar system. All right, so what do technologies do? What should we be looking for? Well, they harvest energy and do work with different levels of efficiency, and it depends on whether it's chemical combustion or geothermal or nuclear, and the observable consequences of those different types of energy. Well, hopefully, if James Webb ever launches, it could detect CFCs and carbon chlorofluorides with something like 2 full days of observing time. How likely that's ever going to be assigned, that will be determined, that is to be determined. If it's nuclear that you're using as an energy source, then fissile waste disposal will become a problem. And if you got rid of it by dumping it into your star, then you could enhance the signature of rare earth elements such as praseodymium. If it's fusion that you're using and you put your fusion reactor in orbit to get it away from your planet and to remove radiation hazards, then when you fuse hydrogen, there's often a little bit of tritium leakage. And tritium has the equivalent of the hydrogen 21 centimeter line at 15, 16 megahertz. And so if you were to find tritium any place except in the vicinity of a brand new supernova with its short 12.5-year lifetime, you would be extremely curious about what was making that. So what kinds of work? Well, we do work for all of those reasons here. And so if you're going to find consequences of information transfer, well, we're now a multi-messenger universe. We transfer information with all kinds of carriers, photons, particles, entangled pairs, gravitational waves, faster than light travel potentially. But for the near future, it's really going to be electromagnetic waves that we're going to be searching. And so what have we searched in terms of looking for electromagnetic communication? So in 50 years, when SETI turned 50, I did this calculation, and we've been looking for, in the radio, compression in frequency and in the optical compression in time. And when I did this calculation and said, let's take all of this, and now we're beginning to look for monochromatic laser beams, not just bright optical pulses. And now this is the kind of thing that we've been looking for in the radio. So there is a signal there from the Voyager 1 spacecraft at 106 AU. And although it might be hard for your eyes to see it in this waterfall plot, which is time vertically and frequency horizontally, once I show it to you, you can't not see it, and our detection algorithms find that as a 6 sigma event. So we also can look for signals that are almost natural. So here's a pulsar, right, at one period, and that's another period. And then what if the pulsar went back to the first period and then changed again? So this is a kind of a signal that's almost natural. We've seen pulsars change their frequencies because of starquakes, but we've never seen a pulsar go between one frequency and a second and back again. But this is exactly the sort of thing that our pulsar searches would uncover, and some graduate student would be scratching their head when they looked at the data and saw this happening. Here's another example. Planets are round by definition, but you could in fact create artificial transits with structures that are huge, but not round in shape. And the high order moments of the light curves at ingress and egress would tell you that that was a shape that wasn't round. Here's another one, Cepheid variables, all right? They expand and contract with fairly constant periods. What if you had a neutrino factory and you could orbit it around a Cepheid variable, and the star expands and then contracts, and then prematurely, before it would be ready to expand again, you zap it with these neutrinos and you cause it to expand. And now you've got the normal period and a short period. And it's a Morse code that information, it could carry information, and these are seen all the way to the Virgo cluster. So almost natural, you in fact could imagine encoding at almost atomic density information in essentially a rock. And if you're not in a hurry, you can throw rocks between stars and they will eventually get captured and hopefully land somewhere that you could find that artifact. All right, so there are 9 dimensions of this cosmic haystack, even if you're only talking about electromagnetic signals. And the question is, how much of that haystack have we searched? So when SETI turned 50, I did a calculation that said if those 9 dimensions are a search volume, and I set that search volume equal to the volume of the Earth's oceans, then so far we have, at 50 years, we have surveyed 1 8-ounce glass out of that ocean. And then Penn State students did the calculation a couple of years ago, redid it when SETI was about 60, and we've now gotten to a small swimming pool worth of observations. And no one would be willing to draw a very definitive conclusion on the basis of that little searching. So we need to keep searching. Another kind of thing that has been suggested is if you're looking for the consequences of transportation, right? They might be going in starships with matter-antimatter annihilation engines. And so when we first began finding gamma ray bursts, we wondered whether they might be the acceleration of matter-antimatter engines producing 500 MeV photons. It's been suggested if you're going slowly between the stars, you might stop off at the asteroid belt to replenish your supplies. And so it was suggested that if we found a small orbiter around an asteroid, we might be suspicious about a spacecraft. And in fact, we've found small orbiters around asteroids, and they turn out to be small rocks. And then also, we are thinking about ways that we could potentially detect the monochromatic laser beams that might someday be used to accelerate small sensors up to 20% the speed of light. And then, of course, faster than light travel, I don't know what to do with that one. So what are the consequences of megastructure construction? Well, something like a Dyson sphere, there will be infrared excess around visible stars. Stars might, over time, disappear because they get encased and go below your detection sensitivity limit. And you might end up with stars that are where the spectroscopic distances appear to be far greater than the parallax distances, simply because the star has been artificially dimmed. Again, we mentioned this earlier, glints from large orbiting mirrors to warm up the dark sides of tidally locked stars. You might be able to see some footprint of resource extraction on exoplanets or in an asteroid belt. And we're now in the place where there's just so much opportunity for improvement over what we've been able to do. The instrumentation, the computing is faster. We're beginning to have access to the transient sky, which we've never had before. AI and neural networks can begin, instead of us asking the machine, do you see this pattern in frequency and time? They can in fact begin to tell us that there's information content of some kind in the data that we've collected. There's all kinds of now opportunities for data mining and commensal observing. And the best thing is that we're now beginning to have undergraduate and graduate school curricula. So the next generation is being trained. So in Northern California, we have built the Allen Telescope Array, and we are using it to do SETI, except right now we are doing an upgrade, so it's not on the air at the moment. But this is the first time that we've ever built a large radio telescope as a large number of small dishes rather than just one big collecting area or a few large dishes. These are 6 meters in diameter. It's an absolutely excellent survey instrument, and the computing is as important as the steel and electronics. So the other big game in town now for SETI is the Breakthrough Listen project. It's Yuri Milner has funded them with $100 million over 10 years. They want to search from 1 to 10 gigahertz. They want to look at 1 million stars. They want to look at 100 galaxies. They want to look at the ecliptic plane and at other exotic targets. So they are operating now on the Green Bank Telescope in West Virginia. on the Parkes Telescope in Australia, on the Automated Planet Finding Telescope at Lick Observatory, and they have signed MOUs with the FAST Telescope in China, the Meerkat Telescope in South Africa, and the Jodrell Bank antenna in the UK, and instrumentation will be going on these telescopes soon. And the thing that we're really excited about is the fact that we're going to figure out a way to put a spigot on the Very Large Array, which is the most productive radio telescope that we have, and be able at the same time, commensally, while other people are observing for radio science, we will be able to take that data and process it looking for engineered signals. There's other telescopes, there's other SETI on telescopes, smaller projects. There's SETI at Home, the thing that put distributed computing on the map over a decade ago, has been working at Arecibo and is currently off the air. They're trying to decide how they're going to go forward with that in the future and take a look at all the data that has been collected and analyzed by people using this SETI at Home application on their computers. LOFAR across the Netherlands, across Europe and the UK has begun to look for low frequency signals. There's a telescope in Italy that is beginning to do SETI work. Down at JPL, they moved one of their DSN telescopes outside the gate and have formed the Goldstone Apple Valley Radio Telescope. And they are actually, the students actually at Gabbard are doing a sky survey. And the Malura Wide Field Array in Western Australia, again, a low frequency array, is beginning to do SETI searches. And in the optical, Harvard has built a dedicated optical telescope to do surveys. All of the data that are gathered from the Keck HiRes for radial velocity studies of exoplanets are reprocessed to look for artificial laser signals. There's an amateur optical SETI observatory in Boquete, excuse me, in Panama, and you can do literature searches. So all the data taken from the WISE survey telescope on the sky have been reanalyzed looking for these Dyson spheres, Kardashev type 2 civilizations, or Kardashev 3 civilizations that can control all the energy from their galaxy. We've recently begun using, that's funded by Breakthrough Listen, begun using the Veritas array, gamma ray telescopes. So four telescopes with cameras at the focus of each of these 4 telescopes. And those cameras have essentially 500 pixels in each camera. And what they look for is air showers. They look for streaks across these pixels, representing a high energy particle entering the atmosphere. But by writing some new software, no new hardware, but by writing new software, we can ask not for streaks, but for single pixel events, where the same pixel on the sky lights up in all 4 telescopes. And then we held a workshop at the turn of the century, SETI 2020, and said, what should we be doing and in the next 20 years? So we're there now. We said we should build our own telescope. We've done that with the Allen Telescope Array. We should move the observing from the radio and down into the optical and infrared. We've done that. And then we should figure out how to be sensitive to transient signals by looking at all the sky all the time and eventually at all frequencies. So we're getting there now. And here are 2 projects. Here's one called PanoSETI, being run by Shelley Wright down at UC San Diego. And basically she uses those 1/2 meter Fresnel lenses and builds a structure that's like a Buckminster Fuller dome, if any of you are old enough to remember those. And these lenses focus a large area of the sky onto new modern array avalanche photodiodes. And so in this example, with 126 lenses, you can sample 10,000 square degrees on the sky instantaneously. And the first of these detectors, the first two actually, starting in January, were kind of jury-rigged, lashed into telescopes at Lick, and they've been undergoing engineering testing ever since. And they're working very well. I should go back and make the point that if you, because this is a transient that you're looking for, if you want to have any confirmation or any real strong verification of a signal, you want to build two of these and have them co-observing the sky to give you a validation. All right, the other project that's looking at all the sky all the time is laser SETI that we're working on at the SETI Institute, right? That's based on cameras, not just not telescopes, but very high grade cameras and grading filters. So 8 cameras at a site sees the sky from 15 degrees horizon to horizon. And you need 2 cameras that are looking in the same direction, because you have your gratings at right angles to one another in one camera and in the other camera, because the way the readout takes place, you sacrifice one dimension as you read it out fast. So this is, say, a spatial coordinate X, and what you're looking for is not continuous signals where the spectrum spreads out, but you're looking for monochromatic pulses that can be as short as a nanosecond. And you look and see those 2 dots, but you have only one spatial coordinate. So you get the second spatial coordinate from the second camera with the grading at right angles. And the first of these systems has been installed in Northern California in Sonoma at the Ferguson Observatory. The next system is intended to be installed at Haleakala. So we have the permission, but we don't have a way of getting there with the quarantine situation. So hopefully that will resolve itself, and then putting something like 15 observatories based on these cameras around the world will allow you actually to be looking at all the sky all the time for pulses that last for anywhere from a nanosecond to a few seconds. And in the future, well, we've got all of these wonderful telescopes coming up that can go looking for biosignatures. The James Webb, the Nancy Roman, and either something called HABEX with a starshade, or LUVOIR, large ultraviolet optical infrared telescope. The future of these things will be determined during the decadal review that will be happening in the next year. And then here's a wild telescope that looks more like a radio telescope than an optical telescope. It's being designed in Hawaii by Jeff Kuhn. The claim is that this would allow you to image the Proxima system, and you would be able to look for biosignatures and deconstruct the light curves. So if you get hundreds of light curves throughout the orbits of any planet going around Proxima, you could deconstruct them to actually see the land masses and oceans. And for optical SETI, well, there are all these wonderful large telescopes that are being built or are now functioning. And we would like to figure out how we can put SETI detectors on these so that we can observe commensally. And that is to be determined, and many of the panel might be interested in thinking about how to do that in the future. We know that we're going to build the omnidirectional sky survey, the panel SETI and the laser SETI. In the radio portion of the spectrum, FAST, the Chinese telescope, is now being commissioned, and Meerkat is going into operation in South Africa. And possibly, if the decadal review is kind. We may get the next generation very large array across the west and southwest of the country. And then if we ever build that exolife finder and can make it work, then you build it out to something called Colossus, which is 80 meters across and would be able to actually image the heat of a city, a heat map of civilizations on a distant exoplanet. So the thing that is important in addition to instrument sensitivity, access to the sky, is longevity. SETI will never succeed unless, on average, technological civilizations survive and thrive for a very long time. Because if that's not the case, you will never get any two technological civilizations co-located both in space, close enough to find one another, and co-temporal, so that they are on the air at the same time over this 10 billion year history of our galaxy. And that's why Philip Morrison used to call SETI the archaeology of the future, right? It's archaeology because any signal you receive will have been generated long ago and taken years to possibly as many as 100,000 to cross the galaxy to your receiver. So it's archaeology, it's telling you about their past. But if you detect a signal, then you know, on average, technological civilizations live for a long time. Somebody else has figured out how to make it through, and so we can as well. We know that it's possible to have a long future. And I really like talking about this subject because for me, when you start thinking about life beyond Earth, when you begin to adopt a cosmic perspective, it has the effect of holding up a mirror to all of us on this planet and say, see you? Compared to something else that evolved independently out there, you are all the same. And I think that this idea that we are all Earthlings, this cosmic perspective, is what is going to be so necessary for us to find solutions to the challenges that we face that don't respect national boundaries. So any of you who want to be part of this, go into your devices and change the profiles that you have there and have the first thing that you say about yourself be that you're an Earthling, and then start to act like it. Thank you.
Thank you very much. Shall we stop sharing so that everyone can see you as we ask the questions?
Yes, but I have to know. Oh,
so first of all, do we have any questions from the panel? I see Leopoldo has raised his hand. Do you want to go ahead first?
Oh, yes. Can you hear me?
Yes.
Okay. Thank you very much. It was a great talk. I'm going to ask the obvious question here. So has anything suspicious been found anytime?
We have had a couple of quite spectacular false positives that kept us excited for as much as a day. But in the end, we were able to show that it was, as it turns out, the SOHO spacecraft orbiting the sun and not something coming from the target that we were tracking. So we have never been able to have a verified detection. Some people talk about the wow signal early in the, I think it was 78 or something like that. But it's never been possible to follow up on that. It's never been reacquired. It isn't, I mean, if I had been running the WOW project, you would never have heard about the WOW signal because there wasn't a validation and independent verification.
So I have a few, sorry, go ahead.
No, thank you, Jill.
So I have a few questions highlighted from the audience. So we had a few questions, for example, from Christian Borgoño and Swastik Chaube, asking along the lines of many civilizations may not yet have reached an advanced enough stage to produce the appropriate radio signals to be detected, or may have already collapsed. I mean, what do you think our chances are realistically for finding signs of life when the window of opportunity is so small?
Well, I tried to address that in my closing slides, which is that unless technological civilizations persist for a long time, then we won't find them, right? They're just not going to overlap spatially and temporally with us. So from that, I take the opposite point of view. I like to think about if SETI succeeds, then we have a proof of concept that it's possible to become an old technological civilization and figure out how to survive for a long time.
Yeah, I think that's a good argument for SETI to continue. I mean, I know it's already been defunded, but yeah, I mean, this has to be a long-term project to really reach far enough that we have any chance of detecting these civilizations. We had another few questions from, for example, David Katzenel and Ernesto Camacho, asking what sort of life do we expect to find, and what really is the definition of life that we used when looking for it in the universe? Well,
there isn't any universally accepted definition of life. It's one of those tricky things. If you're looking for biosignatures, you can look for disequilibrium chemistry. You can look for gases that shouldn't be in an atmosphere unless something is continually producing them at the surface of the planet, such as biology. In terms of mathematicians and not microbes, we look for something that is modifying its environment. And again, for so many years, what we were doing is looking for electromagnetic signals. And now thinking into the future with all of these fabulous telescopes that are going to be constructed and operated with the actual capability to image some nearby exoplanets, we've begun to try and expand our brains and think, well, what might we see that would indicate somebody's technology? So, you know, I've steered away from trying to define intelligence, and I've steered away from trying to define life. But nevertheless, you can think about our observing capabilities and try and figure out what would make you wonder, what would make you go, huh? What's that? Kind of things. And it might indicate biosignatures or technosignatures.
I can see that Hans has raised his hand. Do you want to go ahead? Let's see, I'm going to ask him to unmute. Okay, we'll come back to Hans later if he's still around. Alvaro, you've got your hand up as well?
Yes, I do. Thank you. Well, first, thank you for the excellent webinar. It was quite excellent. But I have a question actually highlighted from the Q&A, and it's from Eric Peredo, and I'd like to give it a twist. We're looking for some signals of, you were telling us about the signals of technology that we could detect, but if there were another ET intelligence performing as SETI in another planet, what are the signals that we are sending to them in order for them to detect us?
Okay, so in terms of biosignatures, it would be the coexistence of methane and oxygen in our atmosphere, because those are such reactive gases. In equilibrium, they would immediately turn into carbon dioxide and water. But it's because of bovine flatulence from cows giving us methane and photosynthesis producing oxygen that we have that chemical disequilibrium in our atmosphere. So that would be our biosignature from a distance. In terms of technosignatures, we don't actually transmit deliberately, or at least not for any more than a short period as a stunt. So it would be our leakage radiation, our radars, our airport radars, and that is harder to detect because we are not putting gain in any direction towards any target, but we are doing this leakage radiation for our own purposes. And also because it's intended to be consumed locally on this planet, we don't put extraordinary amounts of power into those signals. The one exception being the planetary radars, for example, at Goldstone and Arecibo, which are used to actually map asteroids. So those are very strong transmitters, but very narrow beamed and not likely to stay on any particular target for very long. Nevertheless, if you're a really advanced technology, perhaps that leakage, and you're within, let's say, 80 to 100 light years from Earth, you would have had the opportunity to detect these signals and transpond them or send your own signal to us now that you know where we are. And that's a couple of thousand stars.
Yeah, and a second question is, what are the ethical implications of finding life, like if we find intelligent life, and if there's any prepared protocol for that moment? If you have thought, what happens if tomorrow you find a strong signal for intelligence?
Well, all the way back in the 1980s with the International Academy of Astronautics and the International Institute of Space Law, we actually came up with a protocol for the detection, the announcement of, a protocol for what happens. And first of all, we said it should be announced. It should not be kept secret. It is the property of all humankind. And we did this primarily to try and bolster our Russian colleagues, who were very worried that if they ever made a detection, that it would be suppressed. And so internationally, we put together this post-detection protocol, and it's been modified over the years. But one of the things that it says is that the signatories to that document would not transmit a reply until there had been some international consensus about who should speak for Earth and what should they say. And we were unable to say how you get that consensus, but that it was a desirable thing to do. So we've tried, and we talk about it, and we'll see what happens. We hold workshops on this, social implications of SETI and this kind of thing. And we bring in philosophers and religious leaders and historians, all kinds of scholars. And they walk away at the end of it saying, the world will respond to the announcement of the detection of extraterrestrial intelligence in line with whatever belief systems are in place at the time. And you go, we paid your airfare for that? You know, it basically says that it's going to be the cultural environment that is present at the epoch of detection that is going to determine how the planet reacts.
Thank you.
So Katerina had a question next.
Yes, so Jill, thank you a lot. It was very, very interesting talk. So my question is a bit related to the first question which was asked. So you mentioned that it was not possible to validate some signals which you received with SETI. So is it because it is transit events, so they do not happen again? And did you try to use simultaneously several instruments to try, which would help to validate certain events?
Yes. Well, the Ohio State was early days and there weren't any other instruments. So the co-observing was not a possibility. All of the SETI observing that we did during Project Phoenix, we built what we called a pseudo interferometer. So we had a main telescope and we had a second telescope, hundreds and sometimes thousands of miles away. that co-observed the same target. And when we found signals that were interesting in the main telescope, then we reduced the data that had been recorded in the second telescope. And the second telescope was inevitably smaller, but when you know exactly what you're looking for, you can limit the bandwidth and reduce the signal to noise ratio to go looking for that signal. So we did this co-observing all the time with Phoenix, and now, of course, with the Allen telescope array, an interferometer is a great way to get this kind of validation. So you can see that it's moving at sidereal rate, perhaps on the sky, or if it's something that's coming from within the solar system, you'll see another track. But you will have multiple telescopes telling you that they all saw the same thing. And we think that that's a really good way to go. We think co-observing is something that is definitely necessary. As I pointed out, Shelley Wright is not talking about building one of those geodesic domes full of Fresnel lenses. She's talking about building two, so that co-observing can happen.
Thank you.
Okay, so Jennifer also has her hand up.
Yes. Thanks, Jill, for your talk. Jill, you mentioned that in the field of exoplanet, there are many young and female researchers. But we know that this is not replicated in all areas of astronomy research. When you studied your Bachelor of Engineering Physics degree at Cornell University, you were the only woman in the engineering program, as Wikipedia says.
It's true.
Today, many women study engineering, astronomy, physics, but there is still a big gender gap in STEM, science, technology, engineering, and math. But based on your experience as an engineering, physics, and astrophysics student, how did you experience this gender gap? And what advice would you give to the female STEM students who are watching us now in this moment?
Yeah, well, it wasn't a lot of fun when I was in engineering school, and particularly the social mores of the times. I was locked into a dorm at 10 o'clock at night and then couldn't get out until 6 o'clock in the morning. And so my male colleagues were all over in their dorms, and they were sharing the problem sets. You know, you do the odd numbers, I'll do the even numbers, and they were spreading the work around. And I couldn't participate in any of that. I was never part of a team as a student. I wasn't part of a team until I had to lead one as a scientist, and that was not a good thing. So it's better. Obviously, it's better now. It's not perfect. And it's not only gender, but we've got a lot of underrepresented communities that we need to support. One thing that in the studies that I've seen and workshops I've gone to, either in faculty hiring or in graduate school admissions, don't hire a single individual, don't admit a single minority student, but try and admit a cohort so that they have individuals who understand the cultural, financial, family kinds of strains that the particular individual might be facing. You know, if you're just one, it's really hard. But if you've got a group that you can lean on, so think about cohorts for trying to address these underrepresentation issues, and then find ways to allow them to organize into groups that can support others. And just encourage that. Don't make it hard for them. Really make it easy to self-organize and provide additional counseling and encouragement.
Thanks.
Okay, we have a question. We have a question from Sergio.
I think we should take advantage of Hans.
Hans, his microphone working. Great. Hans.
Thank you.
How are you doing, Hans?
Hello, Jill. What an amazingly rich talk. Really amazing. So, I have a couple of questions. One is, of course, we have all the history of SETI also with NASA. So I was wondering what the situation is, whether the winds are changing also in NASA, and also the collaboration on a worldwide stage. You know, you mentioned a couple of telescopes in other countries like MERCAT and even Australia. And so I wonder how you can enlarge your community also outside the United States. I'm sure that many people are interested all over the world, but still it seems to be largely an American-driven project.
Well, let me start with your first question. We'll see whether the winds are changing after the decadal, the US decadal, to see whether NASA gets interested again. There's been a bit more interest. We've held NASA workshops on technosignatures. We've written a lot of white papers for the decadal. Let's see how that goes. And then in terms of global cooperation, SETI is turning out to be one of the science case subclasses for many new telescopes. And certainly the MERCAT collaboration with Breakthrough Listen, and then their MOUs, although not yet instrumentation, with Jodrell Bank, with FAST, and is allowing for some coordination. It's basically, where's the funding going to come from? You know, I'm not sure that funding agencies in other countries yet have an appetite. We've written some observing proposals with Sardinia radio telescope, but there's not really a funding stream for SETI that I can point at in other countries. On the other hand, the exoplanets and the extremophiles just make it so bloody obvious that there is a lot more potentially habitable real estate out there than we ever imagined when we started. So, I mean, and there's a lot of funding and a lot of interest in looking for biosignatures. And so it's just the next obvious question. Is there's habitable real estate? Is it inhabited? And is any of it technological? It's no longer, we stand out like a sore thumb asking this "are we alone" question, because now it's just the natural extension of searching for life on other worlds, which is now mainstream science.
You're muted, Hans.
I'm here. Can you hear me?
Yes, now we can.
So there's all sky, all the time, all frequencies. That is a lot. So yeah, I know. So I'm wondering whether you have a feeling what is the most promising avenue. You know, I mean, the first question would be, if we receive signals that would need a lot of power also, a lot of terawatts or gigawatts from a foreign civilization, or is a targeted approach better than an all-sky approach, or what is your feeling? I had a feeling from your talk that you were thinking more about all-sky.
Well, because that's what we have not done. Over the decades, we really have had no sensitivity to transient signals, and there are many models that could produce a transient. And I think now we have the compute power to do that. We couldn't try it in the past. We just didn't have the computational capabilities. And now we do. And I'm particularly eager to do the all sky to see if there aren't some radio counterparts to transient phenomena that have been found at other wavelengths. And if you're looking at all the sky and it's strong enough, you'll find it. So yeah, it's a nice exploration piece, not only looking for engineered signals, but to see what kind of astrophysics might be going on. You know, these fast radio bursts that last a millisecond or something, or so, that we yet don't have a really definitive model for. There's something like 10,000 of them going off on the sky every day. And if we were looking...
What about masers?
I'm sorry?
Masers.
Yes, those aren't quite so transient. I mean, they do change over time, but yeah, the fast radio bursts are a mystery. And if we had something that was capable of looking at all the sky all the time over a wide range of particularly radio frequencies, we might be getting farther along to understanding the physics. Now, CHIME, which is a telescope that turned on in Canada this year, you know, it's detecting dozens every week. And for those that repeat, although they don't do it regularly, the repeaters, we are beginning to be able to use widely spaced telescopes on the planet to localize those to distant galaxies. And of course, the disappointing thing is, well, if it all turned out to be faint blue galaxies and star-forming regions, that would be telling us one thing, but we're finding them in where we can localize them. The galactic environment is different. So, yeah, eventually we'll get there. I mean, we've been 20 years since we wrote that report, getting to the start.
Let me point out one little thing to finish. I just read an article by a journalist, I suppose, Madeleine O'Keefe, yesterday or the day before yesterday, about all these new avenues that you have described, to some of them that you have described. So you might be able to find it by Google somewhere. I think it was in Ars Technica.
Yes, I worked
with about it.
Yeah.
Yeah, it was a good article.
It was a good article, yes. We put it out.
Thank you.
We distributed it on social media from the SETI Institute.
Okay, thank you very much.
Okay, Sergio had a question.
Yes, I was wondering if resource were no limitation, what do you think would be the best system or telescope you could think of?
Well, if you're talking about the radio, I'm very fond of interferometers. And so the square kilometer array, which hopefully will get built in the next decade or so, and perhaps the NG VLA on the slightly longer time scale. And for right now, I'm very excited about this spigot that's going to be built for the VLA in Socorro, New Mexico, because at centimeter wavelengths, that's actually the most productive telescope that we have. And to be on the air all the time, although not able to point the telescope, we just look at the data that others are taking from different regions of the sky. I'm excited about that.
I think Thomas had a question.
Yeah, so there is also a little bit of stimulating background here in the Q&A about the red spirals that were found recently, right? So the infrared access galaxies that are basically looking somewhat Kardashev scale 3+, right? Could you tell us a little bit more about that?
I actually can't. I mean, I know what you're talking about. And Jason Wright looked at the WISE survey data, looking for those kinds of phenomena. I don't know who in the community is investigating those red spirals. But I need to find out.
Yeah, I think that's, in my view, that points me into a slightly, I don't know, curious aspect of this search in general, because we are always thinking, coming from this singular planet civilization, right? Why don't we look for, you know, Kardashev scale 2+, let's say, environments, right? That might actually deliver the signal to noise, and we will have much more discovery space if we just could go deeper, not only in volume, but also in time.
Right. So now that we have the computational capability to do a lot of data mining, people are thinking about how to build neural networks that will go through and ingest all of these archival data, looking for information. I mean, it's really hard. The thing that's always been a stumbling block for me is, how can you, unless you generate it yourself, how can you train a neural net that has a known null result, right? How, since you've not looked at these data in the past, as again, unless you generate them yourself, how can you guarantee that this is a null, that there is no information in this signal that you're using for training? But that work is starting to happen, and that's it. I think it's really exciting.
Very exciting, that's true. Yeah, and somewhat along the same lines, there is this, you mentioned Przybylski star.
Yes.
Is there any other similar star of that kind, these trans-uranium, let's say, stable island decay processes or daughter species that show up in some atmospheres? Are you aware of anything else?
I'm not. I mean, Przybylski star was something that I really enjoyed discovering or finding out about, but I'm not aware that there are other outliers. However, again, the thing that I think is going to be really interesting, and there are already starting to be some results, is now that we've got really good distances from Gaia, looking for those cases where the spectroscopic distance of a star is greater than the Gaia parallax distance. And people are beginning to make lists of outliers of stars like that. There's a group in Sweden who's working on it.
Yeah, certainly the archival data volume is just tremendous for starting, right? Any kind of that type of research.
Right.
I want to ask you one question that is really bubbling up here in the Q&A, and so what about the ethical concerns, not only about, you know, detecting contact, the implications of this, but exporting our life, right, to other biospheres? You were talking about the moons of Jupiter and Saturn. What do you think about just simply going ahead, right? We want to immortalize ourselves by sending these probes everywhere, right, and putting these golden records on spacecraft, but we are afraid of exporting our DNA to other biospheres. What do you think about that?
Well, first of all, you need to understand whether there's any indigenous life there, right? I think the question cleanly splits between whether the planet is already inhabited and you're going to try and add human life or terrestrial life to it, or whether the planet is in fact devoid of life and you're going to bring it to life for the first time. And yeah, lots of ethical questions, particularly with Mars, since we're there and we're bringing bugs, we're bringing biology to that planet every time we have a rover hit the surface. And so the ethical questions, should we leave, if we find out that there are Martians, should we leave Mars to the Martians? I don't think that that Mars is going to be a good plan B for Earth, because I think if we don't figure out how to solve the problems of planetary husbandry here and make our planet have a long future with life on it, I think we'll just recreate the problems when we go somewhere else. So whether we should leave Mars for the Martians is a subject that gets quite a bit of discussion. And
it's a tricky one. It's a tricky one, yes. Evelyn, would you like to take another one from the Q&A?
Yes, I've got two more from the audience that I thought we could wrap up with. So they're both in Spanish, so I hope I've got the translations correct. The first is from Arnulfo Tellez, who is asking, is there any fields or areas of investigation that hasn't yet been researched with the SETI data that could still be researched?
There is not from the projects that we did at the SETI Institute, because our signal detection was all near real time. But the Breakthrough Listen group has lots of data that they have made publicly available, and anyone can start trying to build AI or neural nets to look for different kinds of signals in the data that have been previously looked at. So there's data from Green Bank Observatory and Parkes Observatory, and it is publicly available in vast quantities. I think that we haven't done a very good job at looking at the neutrino detectors and thinking about what they may have found that maybe got ruled out as not being a believable detection because it had some strange characteristics, but those strange characteristics might just be because it's an engineered signal and not an astrophysical signal. So I think there's data that is really pretty low-hanging fruit.
And my final question is from Edgardo Quintana, who is asking, what can we do to bring the information that has been found with SETI to schools in a better way? How can we improve the outreach effectively?
Okay, so SETI Institute had grants from the NSF and NASA to actually create a curriculum that we called Voyages Through Time for 9th grade. And it was a year-long curriculum, and it did this whole cosmic evolution all the way through the evolution of technology that got a lot of adoptions and a lot of excitement. Now, it was delivered on CD-ROM, because that's how long ago it was. So getting that into the web environment is a project that we've been trying to find time and energy to get done. And of course, update it, because the science has changed over since we first published that. I think that this kind of format, this webinar format, my daughter is now 50, so I don't have any young people at home that I'm watching interact with screens in terms of an educational endeavor, and I'm not sure how well it's working. But if indeed it is working, then I think that this is a really delightful opportunity to allow classes to get involved. And I would think that having even classes in adjacent schools or neighborhood schools, or maybe across the country, making teams and trying to use the materials that exist for SETI in some kind of a competitive, or something where there's a goal and you want to get there first or get there best is maybe something we can do. And we actually have an education and outreach component of the SETI Institute. And so Simon Steele is the director of that. And these questions should really be getting posed to Simon, because he's thinking quite hard about how to do just that. Again, it will be with an American point of view, and it might not work elsewhere, there are things that may be being tried elsewhere that we would love to learn about and incorporate them into what we're doing.
Cool.
Well,
Okay,
with one or two Patricias more, we can do this across the planet to translate into different languages.
Yes. Yeah. How did that go, Patricio? Did you get tired?
Patricia is doing excellent, I think. I think this has a great potential to break down barriers of many, many kinds.
Yeah.
Well, let's wrap up before we burn him out. Okay, so thank you everyone for joining us today for Jill's talk, and thank you especially to Jill for taking the time to tell us about your work. All the talks in this series will be added to the Astrofísica UC YouTube account in the coming days with both English and Spanish soundtracks. These videos will have a higher quality than the live stream. The next scheduled talk will be on Wednesday, on the 29th of July, and we'll have Jocelyn Bell-Burnell, the discoverer of pulsars, telling us about her discovery. So yeah, there's nothing left to say except thank you all, and see you all on Wednesday. Ciao.
Bye-bye.
Bye-bye, thank you.